Welcome to our presentation on formal analysis and implementation of the TPM 2.0-based direct and anonymous attestation scheme. This is a collaboration between the Department of Computer Science at the University of Surrey, the Department of Computer Science at ETH Zurich, and Ericsson in Finland. The overview of our talk is we're going to give a quick introduction to the problem we are trying to address. We then give details of our main contributions, and we conclude with our conclusions and some future work. Establishing the trustworthiness of laptops, smartphones, or Internet of Things devices is very difficult. Trusted computing is an approach that provides a root of trust, and these roots of trust can then be used to attest that devices are in a trustworthy state. A trusted platform module, TPM, is such a root of trust, and it provides cryptographic primitives and secure storage. The Trusted Computing Group, TCG, have defined TPM commands for a range of services, for example, signing platform configuration registers, keys, clock, time, and audit digest data. These are then used to prove the trustworthiness of such devices. What we also want is that these schemes should offer user-controlled security and also be privacy preserving, so that you can't know who sent or signed the message, but you can still verify that that message is valid. Direct Anonymous Attestation, DAA, is an anonymous signature scheme that provides these facilities, and moreover, it can also use these TPMs, which are embedded into pretty much all new laptops and modern desktops and smartphones. So combining those two is what we want to do. Chen et al. Defined an ECEC DAA scheme in terms of these TPM commands and provided also a computational security proof of the TPM side operation in their paper. However, their description lacks implementation level detail, which is what we are trying to address in this paper. So our main contribution are we're actually providing the TPM 2.0 details that were missing in Chen et al.'s paper, using the latest version at the time, version 1.38 of the TPM specifications. There have been updates since. We also provide a formal analysis of the scheme using the Tamron prover, and describe the authentication and security properties required by the scheme in Tamron. We also finally provide an open source reference implementation that implements this scheme and benchmark it, which can then be used as comparative benchmarking for future development of ECC DAA schemes using TPM 2.0. So the main contribution number one was to actually translate the original specifications into a API level version that can be used by implementers to start coding. And the original paper defined 5 operations: setup, join, sign, verify, and link. And in this paper, we are providing the join, sign, and verify protocol specifications. The setup is a one-off process that's not of that much interest, and link is pretty much just checking a certain value, and again, it doesn't require any API level specification at that point. We should note that the sign operation actually has been extended to 3 different contexts. So signing a message is the original sign, certify, attest another key generated by the TPM, and quote, attest the platform specific values confirming the state of the system, which is the one that establishes the trustworthiness of a platform. And we provide enough details for these for implementation, mainly because we use that ourselves to implement our scheme. Here's an example of what we mean by enough detail. I've picked the sign operation mainly because it's small enough to fit on a slide. Obviously, before a sign can happen, you have to go through the join, which establish all sorts of values which are used in the sign operation. But at the end of the join, the host has got these values, the TPM has got certain other values, and the user now wants to sign the message M. So the host computes some hashes and fires them over to the TPM, which then constructs its own versions of hashes and some other values which get sent back, which then the host feeds back into the TPM to sign, which then does some verification, and in the end, the actual signature pops out at the other end, and the host can now send the message that was to be signed with the signature containing numerous values. As you can see, there's enough detail as to what needs to be inputted into the various operations on the TPM, and it also explains what the calculations are that are carried out to work through the ECC DA scheme at an implementation level. And we've got sufficient details of all these operations in our paper, and I'll refer you to those to have a look. We're now going to embark on the formal verification side of things. Before we do that, we need to introduce some DA terminology. We've got a platform which describes the unique one-to-one combination of a host, i.e. your laptop, and the TPM. The TPM should be inside that. We use a message to represent both a signature, a certified key, or a quoted PCR value that can then be verified by the verifier. So these are the things we can sign, and the signature gets then sent across to the verifier to check. And the other thing that you need to bear in mind is the TPM inside your laptop is the only trusted element. The laptop is assumed, or can be assumed, to be untrusted. But the scheme should still work even in that hostile context where the host is untrusted, but the TPM is the only root of trust. As part of DA, or formal verification of DA, we also needed to look at the various properties that are associated with DA, and we based those on Chen again. And the main ones are correctness, which is just saying that the scheme works as intended. There's nothing strange about it. So it's just saying that if you start off with the right values and you want to end up at the end, you can actually get there. And then you've got user-controlled traceability, which consists of user-controlled linkability, so a user can control whether messages should be linked, and unforgeability and non-frameability, so messages can't be forged or they can't be claimed to be from someone else. We've also got user-controlled anonymity, where the user can decide that they don't want to be recognized, and you've also got user-controlled unlinkability, that it's still anonymous, but you can now say that messages that are sent from a host or from a platform can now be linked. So we still don't know who they come from, but we know they come from the same one. And the last one we introduce is the agreement during the join. And that just means that both the platform and the issuer confirm each other's identity and agree on the credentials that were created during the join operation. This is important because that's where we found an issue in the current specification. We propose a fix for it. Our threat model that we assumed is similar to what Kamenish proposed. We assume that the TPM is responsible for securely deriving the keys, and the host can be untrusted. We've also got an issuer and a verifier. The issuer is a trusted third party, but even so, we also assume that there might be some corrupt issuers. Again, the TPM is assumed to be temporal resistant, but again, in our models, we do allow for some TPMs to be corrupted to see whether or not we can use that information to provide attacks that would normally not be possible as such. The channel model that we used, again, is based on Kamenish's assumptions, where the link between the TPM and the host on the platform is completely secure. So your laptop and your TPM use a secure channel, and any adversary doesn't have access to that channel. Obviously, the host might be corrupted. The host knows what it's sending through, but even if there's a trusted host and then an adversary on the host, they can't see what's being sent as part of that communication between the host and the TPM. On the other hand, the channel between the platform and the issuer and the verifier is completely in the hands of the adversary. We use the classical $VL model where $VL can intercept, read, manipulate messages at will, but the adversary can only decrypt messages if they actually have the key or can derive the key as part of the message exchange that's happening. So we then started encoding our scheme in Tamron, and Tamron is a state-of-the-art protocol verification tool which has been used widely in protocol specifications, verifications, and has been very successful in that, which is why we chose it. And protocols are written using multi-set rewriting rules, and any property that you want to prove is encoded usually using first-order logic, whereas anonymity properties are usually encoded using the observational equivalent mode of Tamron. And another advantage of Tamron is that it uses the standard $VL adversary model for its channels. So what we then did, we used our specification and faithfully tried to map all these calls that are happening into the appropriate Tamron models. So if you look at the Tamron model, you should be able to see, using the name convention, we used that there's a one-to-one mapping between the Tamron model and the actual specification that we have. So the join operations that you see in the paper as a specification, you'll find pretty much identical naming in our Tamron models to make it easy to see how they're linked. We also encoded all these 7 properties we spoke about using first-order logic or observational equivalent proof mode, and as a result created 18 models to allow us to prove these properties. Why 18 models and not just one? Because of the complexity of these different rules and the size of the models. It's computationally infeasible for Tamron to go through these at the same time. So what we split all these different models and operations into separate files. So we've got a model for the sign operation, we've got a model for the certify operation, we've got a model for the quote operation, and prove these various properties inside those separate models. And for the observational equivalence, i.e. the anonymity requirements, we had to use separate models as well to make that computationally feasible. As you can see, the models are further split into 2 between signatures using a base name, which allows linking, and signatures not using a base name, which doesn't allow linking. And the same thing for the observational equivalence modes. So in the end, we ended up with 18 different models that we had to analyze. The main challenge was to cast the various properties into the Tamron way of speaking, i.e. the first order logics or the observational equivalent mode. I refer you to the paper for the details of how we did it, how we justified that the security properties are what they are in Tamron, and why we believe that this is an appropriate way of phrasing these. Having done that, we ran the models. We needed to create some oracles for Tamron to help the prover go along, but this is sort of a standard practice in very complex models. And luckily, what turns out is that all but one of these security properties proved successfully. And the one that didn't prove was the one that we introduced separately due to the findings of Whitefield and al. In their analysis of a similar scheme, which is described in that ISO standard here on the slide. They found a flaw, and we believe that same flaw was actually present in the specification that we provided based on Chen's paper, and it turned out to be the case. Luckily, the same fix that Whitefield and all found also applies in our model. So to fix the attack, which effectively says that the issuer and the platform can't confirm the identities and don't necessarily agree on the keys that were issued, which is obviously a major flaw. The inclusion of the public endorsement key of the TPM epsilon in the proof of knowledge that goes on as part of this join phase. If that is included, that also stops the attack in our model. And that fix works even though the channel between the platform and the issuer is insecure. Going through the implementation side of things now, implementing it, as I said before, was not straightforward because we provided all the details that are needed. We wrote roughly 7,900 lines of code, and we tested this on 2 platforms, the Raspberry Pi and with an Infinite TPM chip, and an Intel laptop with the calls being implemented by the TPM emulator by IBM. We only present the Raspberry Pi results in the next slides because the TPM emulator just produced the same timings all the time. So they're trying to obfuscate the actual timings that these calls take, probably to prevent timing attacks. We ran these operations 200 times to find out the decent average, and the results are presented here. The one that is worth pointing out is that the pairings checking on the Raspberry Pi takes a significant amount of time, but it is known to be a slow operation, and that's what we found too. I'll leave you to look at the numbers for the various TPM calls to see how they differ. But if you look at what actually goes on behind those, it's not surprising, given the amount of work involved in the TPM, obviously being a resource-constrained small chip. Again, the sign and verify operations show that having a base name as part of your signature to actually allow for linking is more expensive, because it also, if you look at the maths behind it, it requires 3 exponentiation instead of just 1, which makes a linking signature operation an expensive operation. The other thing to note is that the other signing contexts where you certify and quote are shorter because they don't require the hash be computed first, because they are not generated by the host, they are generated by the TPM itself, so it knows that already. So it doesn't require as much time. The verification of the different signatures in the various contexts are pretty much all identical, slightly slower when there's a base name involved, but not significantly so. So to conclude, we've presented a fine-grained details of a DA scheme, ECC DA scheme on TPM commands, which extended to include the certify and quote operations. We produced numerous formal Tamarind models of these ECC DA scheme at the level of TPM 2.0 calls to make sure that it's a truthful representation of the scheme. And all the relevant ECC DA properties have been formalized and verified in the symbolic model once we've included the fix. And this is the main point we're trying to state here. The verification of the model shows that the Whitefield and all attack also works for us, and the fix for it works for us too. So we recommend that the TCG incorporate this fix in the future, rather of the TPM justification. We've got a reference implementation available for people to test and run with, and it shows that signing with the linked, with the requirement to be linked, is an expensive operation. What we would like to do is apply this approach also to other new areas like the web-based authentication scheme like FIDO, and also intelligent transport systems, as well as vehicle-to-anything communication, which also requires anonymous signatures and anonymous credentials. So this could then be used to sign V2X messages and other identities that can verify the messages without prior knowledge. This concludes my talk, and I'm happy to take now any questions. Thank you very much.